God. Okay, so following up on what we just saw, we were working with the Atwood machine. Please rewind or take a look at the previous video to check that out, but here's the Atwood machine. We hang two masses. We have a thin, light string that goes over a pulley of negligible mass and friction. Basically, we're trying to keep these things small so that they don't have a huge effect, and we found an equation for the acceleration. We found the following, that the acceleration, or at least the magnitude, I should say, so the number, can be found by taking the acceleration due to gravity times m1 minus m2 divided by m1 plus m2. Now, we went through and we did it the thorough way, and there are some upsides and downsides to it. First off, the thorough way, if done properly, pretty much always gives you the correct answer. And so if we made this a more complicated problem where one of them was on an inclined plane and then it had friction, or that we had a bunch of other weird stuff going on this, frictionless tables and so forth, we might have to adjust things and it might get a little bit trickier. But going through and doing it will still get you the right answers if you've got it set up properly. There are a few things that I'd like you to take a look at, though, and be aware of. You don't have to solve things this way, though you might want to do so, because it's actually a little bit easier. What I want you to imagine is this. We've got our two objects, one here and one here. And when we let go of them, depending on what their relative masses are, this one goes down, this one goes up, or this one goes down and this one goes up. And they have the same delta x, they'll have the same velocity at any given point, at least all things being equal. And they're going to have the same acceleration, which is what we found here, the magnitude of their accelerations. In short, they're tied together, so all of their kinematic variables, all their kinematic values have to be the same. If this one goes down by a foot, this one will be pulled up by a foot. If this one is going 1 meter per second down, this one will be pulled up at 1 meter per second. Same thing with the accelerations. Whatever one has, the other will have as well. And we talked a bit about this in class. We did this when we were looking at Cleophas, the train car, and actually dealing with pulling on a train that had multiple cars. And I told you that there were some things that we could do that were actually kind of clever with it. If we don't care about the force of tension between these two, just like if we didn't care about the force of tension between the two train cars, we could actually combine these two objects into one object. The difference between object and system basically boils down to, do you care about any internal structure? And since this one, if this one goes down by a certain amount, this one will go up by a certain amount. Here's where you're going to have to get a little creative, though. To make things much easier for us, I want you to stop thinking that we've got it where this one goes down and this one goes up, even though that is technically reality. But if we make this one object, we could say that, well, instead of up and down, I want you to imagine that we are instead of this, I want you to imagine instead, maybe we're on a flat, frictionless table, and it's like this. If this one goes down, you could imagine it going to the left, and if this one goes down, it's going to the right. So I've got these. If this one does this does that, or this. Now what I'm doing is I'm pulling the strings up, and if this one goes this way, which would be the equivalent of it going down, that one goes this way, which for it would be the equivalent of it going up. In short, what I'm doing is I'm taking something that is wrapped around like this, which is what a pulley allows you to do, change directions of forces, and instead of having it go in a horseshoe, I'm actually just flattening it out. This one goes this way, and the other will go this way. This one goes this way, and opposite. Now, this takes a little bit of creativity and imagination. That's one of the downsides of this. On top of that, sometimes when you start thinking about things differently, it might start hiding some of the reality of it. So I'm not going to say that this is the best approach for every single problem. The thorough approach always works. But let's go through, now that we've got this set up, if this one goes down, that one goes up. If this one goes down, that one goes up. And so what we've got is, they keep doing something like this. Oops, sorry. If this one moves this way, that one moves this way, and so forth and so on. So if we've got a string between them, string between them, instead of having it like this, I could instead have it like this. All right, Now that we've got that, I don't care about the internal structure of this thing. I don't actually care about the force of tension. What I've actually got, if you want to think about it, is imagine we're on a frictionless surface and we've got an object here of both of the masses put together. I'm going to put them together as one giant object, just like we did with the train. Now, the mass of that object is going to be m1 plus m2. It's the combined masses of both of them. And now, what I want to do is I want to imagine it moving left or right. Well, if I've got it set up where this is m1 and this is m2, and I'm bending them like this, if m1 gets pulled down, that's the same thing as moving to the left. If m2 gets pulled down, then it's moving to the right. Basically, what we've got here is gravity is pulling on these things, and it's a tug of war. If m1 is bigger, then this side has more gravity and wins and pulls this down, the other goes up. If m2 is greater, then gravity on this side wins, pulls this down, and that one goes up. In short, I want you to imagine gravity's pulling on both of them, and which way it goes is a function of which one is being pulled on more. Now, we've got it pulled like this. I want you to think of it literally as a tug of war. Gravity is pulling on one side, and gravity is also pulling on the other side. What this thing will do will depend on which side is being pulled on harder by gravity. And gravity pulls harder on things that have higher mass. The force of gravity depends on the mass. So, I imagine my free body diagram. I know on this one, I have the force of gravity of object 1, and over here I have the force of gravity of object 2. Now, I draw them to scale, but at this point I haven't decided which one's bigger, if either of them, or more massive, I should say. But in short, I've got a tug of war between the force of gravity on this one and the force of gravity on this one. Well, that means that I've got a force of gravity trying to pull it one way, and another force of gravity trying to pull it the other way. All right, well, I'm going to do my sum of forces. Now, I will still need to keep track of the directions in this, and I've played a little fast and loose with them, but I want you to imagine this. It's like a tug of war. If this side wins, this goes down and that one goes up. If this side wins, it goes left and this side goes left. They both move as a result of which side is winning. All right, so if I do my sum of forces, well, let me switch this over to red, because I've got blue here because they're vertical, but now in my weird, distorted way of looking at it, they're actually in kind of an X direction. And since they're not actually touching anything, I don't need to worry about what's going on in this direction. Yes, the way that I've drawn it, there'd be a force of gravity here and a normal force, but those aren't actually there. I'm looking at one object that's being tugged on in two effective directions. Even though they're both being pulled down, I mentioned in class that tension is neat because it allows forces to change direction. And with this compound problem, we can simplify it thinking of it's a tug of war between gravity on these two things. Bear with me. So if I do my sum of forces, I'm going to have, well, let's say that this way is positive x. I'm going to do positive fg2 minus fg1. Minus, because this one's to the left, that one's to the right, great, equals our mass of our object times the acceleration, well, in the quote-unquote x, but in this case, we're finding out what the acceleration is going to be of this object. Okay? Well, let me fill this in a little bit. It's weird to see gravity in the x direction, but we can set things up however we want. So this will be m2g minus m1g equals the mass of the overall object, because remember, this is the force of gravity on 1 and 2, so this is 2, and this is 1. I've got them that they're pulling in opposite directions, so now I've replaced those. But this mass is for the total thing, so it has the mass of both of them combined, m1 plus m2, times our acceleration, whatever our acceleration happens to be. Now, out of habit, I put the x here, but we know that it's not actually in the x because we're moving forces around. But in the end, conceptually, we've got a tug of war between these two, gravity pulling on both sides. And it will move, both of these objects will move based on which side is winning. Okay, well, if I want the acceleration, here's my force of gravity, one of them pulling it this way, other force of gravity pulling it the other way. Those are my forces acting on it. And here's my combined mass. There's my acceleration. Well, if I'm solving for the acceleration, I just divide by m1 plus m2, and I get that the acceleration is equal to m2g minus m1g divided by m1 plus m2, which is effectively the same thing that I got last time. There might be an offset of a negative. That's where the absolute value comes into play. Remember, what this is actually telling us is what the magnitude of the acceleration would be. We'd have to keep track of which one goes which way. But I can factor g out. I end up with g, m2 minus m1. We have the difference of the two masses, one of them minus the other, divided by m1 plus m2, divided by their combined mass, which is the same thing we got the thorough way. Now, the thorough way, the way that I had set it up, I had m2 minus m1, but again, negative, if we flip these and have a negative, that's just going to change which direction they move. So, the key thing that we're looking for here is we're finding the magnitude of this. The magnitude of this is equal to the magnitude of our acceleration. It's a way of finding the number. Let's double check it again. Let's just do it mentally this time. If m1 equals m2, then both of these are the same. It goes to 0. We have an acceleration of 0. They don't go anywhere. If one of these is effectively 0, so if we have m1 is basically 0, then it's m2 divided by m2. Those cancel out, and we are left with the acceleration will be equal to g. You can also check your units, but we can see that the units actually come out as well. I don't know if this is helpful for you or not, but a lot of times when I'm looking at objects like this, even if I've got several of them, when they're tied together, I like to think of the forces that would make them move one way or the other, and I set it up as a tug of war, one side pulling and the other side pulling, and looking at which side is going to win. That way we can cut out some of the middleman, and you can see we actually reduced a lot of the equations that we needed to work with. We've got this force trying to pull it this way, and this force trying to pull it the other way, and we set that equal to the total mass times the total acceleration, because they both have the same magnitude of acceleration. The signs, the weird negatives that we may or may not have show up in there, is just because one goes down and the other goes up. All right. So this is the slightly simpler version, depending on your viewpoint.